This is the first of 2 lectures on glacial processes and landforms, and I want to begin with the Ice Age, when it occurred. I've got a geologic timeline showing you when the Ice Age occurred and the terminology that's used. In geology, the name for the Ice Age is called the Pleistocene, and it began about 3 million years ago, and here we've got this long time span and ended about 15,000 years ago. From 15,000 years ago to present, we are currently in a geologic time period known as the Holocene. Let's look at the detail of the last 3 million years. Now, the Pleistocene was not 3 million years of just totally freezing cold climate. Actually, it was characterized by alternating cold climates and warm climates. Now, the cold climates were when the snow and ice would accumulate. And basically, there was no summer during these glacial cycles. So you'd have snow accumulating during winter time, and it would not melt back in summertime. And you do that year after year, and you accumulate snow that ultimately compacts and turns into glacial ice. Now, it's generally agreed that there were at least 4 glaciations lasting on the order of hundreds of thousands of years. So I've got 4 G's here representing at least 4 glacial cycles. Now, the warm cycles were called interglaciations, and interglaciations are pretty much climates like we have today, where the snow of winter melts back and melts away in summertime, so we don't wind up having the continuous accumulation of snow and ice. Now, the interglacial periods were much shorter in time span, typically on the order of tens of thousands of years. So I'm trying to show in these shorter warm cycles or interglacials. Now, the important thing that we need to make note of is actually today, the Holocene is an interglacial cycle. So the last big ice sheets were pretty much melted back by about 15,000 years ago, and we're in a warm cycle called the Holocene interglacial. And if you really kind of take a look at the pattern of the last 3 million years, what's going to happen next? We're actually due for another glacial cycle. And there has actually been talk about, another glaciation offsetting global warming. But that's not anything that we're going to see in our lifetime. If there is another glacial cycle, it won't happen for another, 10 or 20,000 years. So it really won't affect us in our lifetime. All right, let's kind of move on and just talk to you about the 2 basic types of glaciers. The first type are called ice sheets, and these are, masses of ice, of continental dimensions. And there are 2 active ice sheets on Earth today. Now, in the northern hemisphere, over Greenland, we've got the Greenland ice sheet. Now, this is not located at the North Pole. Now, the North Pole is the Arctic Ocean. There's no land over the North Pole. You've got to have land for, snow and ice to accumulate. So Greenland is the highest latitude location where we have land, and thus the accumulation of snow and ice. Now, of course, we do have land over the South Pole, and so the second, active ice sheet is over Antarctica. Now, the other type of glacier occurs in high mountain areas, and they're called alpine glaciers. And during the Pleistocene, there was certainly the growth of alpine glaciers, and many have since melted back, but there are certainly a lot of fine examples of active alpine glaciers today. What I want to do now is show you the ice sheets that grew in the northern hemisphere, the land hemisphere over North America and Eurasia during the Pleistocene. These have since melted back, so we're going to talk a little bit more about these Pleistocene ice sheets. Right now, like I just said, that they grew in the northern hemisphere, the land hemisphere, at high latitude locations, where it was colder, over North America and over Eurasia. So let's just talk about those 2 big ice sheets that have since melted back. So the one I was just showing you here of North America is named the Laurentide ice sheet. And it began to grow about 3 million years ago. It's believed to have started somewhere around Hudson's Bay, and it advanced. And it's got the arrows showing the advancement. And so today, it's all melted back. It's gone. And probably today, the Greenland ice sheet is probably the last shrunken remnant of what was once the Laurentide ice sheet. And there's the North Pole. So, again, it's the Arctic Ocean, so there's no land there. All right, so this ice sheet covered virtually all of Canada, right, extended into the United States in the upper Midwest, New York, and New England. Now, the southern limit, right, the farthest, extent southward that the Laurentide ice sheet ever went, represents the current courses of the Ohio and the Missouri River. Those two rivers formed as ice margin streams, draining meltwater from the glaciers flowing down slope. Now, these two rivers met, right, and then formed, and a valley formed, and that actually created the Mississippi River. So the Ohio, Missouri, and Mississippi River all formed during the Pleistocene. And as we know, the Mississippi River was the major glacial outwash stream, melting all of this huge mass of ice. The Laurentide ice sheet was believed to be at least a mile thick. Now, there is a kind of an interesting area, mostly in Wisconsin, that was never glaciated. So there were 4 glacial advancements over 3 million years, and during those 4 glacial advancements, constantly missed this little area in Wisconsin, and it's called the driftless area. And it's called driftless, but if you remember the term drift, when we were talking about literal drift, drift is just a general term in geology for sediment or sediment movement. And in this case, they're talking about glacial sediment. And so this is an area where there's no glacial deposits. And this is how we kind of know where the glacier was, because there were glacial deposits here. And so it's a kind of an upland area of sandstone, kind of delicate sandstone features. And so here's the sandstone arch. We hiked to that, and in the driftless area. And here's some delicate sandstone buttes. Now you can imagine what a mile thickness of ice would do to this. All right. The evidence is that what the ice would have done, was just plowed right on through, eroded this, and incorporated all of this into the ice. And so these features, are evidence, right, that the ice constantly missed this area. Now, the Laurentide and ice sheets had no problem covering, going right over mountains. I mean, I've talked about the Adirondack Mountains in New York State. I mean, there were 10,000-foot mountains at the time, and the ice just moved right on over and carved them, to half the elevation today, about 5,000 feet. So, so how did 3 million years and 4 glacial advancements constantly miss this one area, surrounded? And the explanation is the frontal movement of ice sheets kind of moves as lobes or tongues of ice. And it's believed that during the first glacial cycle, these tongues or lobes of ice carved out the land, eroded the land deeply. Right? And so then it melted back during an interglacial, and then there was a second glacial advancement, and the ice just followed the same path. And it just so happened that the glacial lobes missed this one area in Wisconsin during the first glacial cycle, and so all subsequent glacial lobes missed this area time and time and time again. All right, yes, so there was another ice sheet that grew over Eurasia, and it's called the Scandinavian ice sheet, mostly of Europe. So it began originated over the Scandinavian peninsula, and then it advanced and grew over land. So a good bit of northern Western Europe, Germany and Poland, and of course a good bit of Russia too. Right? And also interestingly too is the British Isles were also glaciated. So if you ever go to Scotland and a good bit of England and Ireland, you'll see some glacial features. But noteworthy, southern England was not glaciated, so London was not covered by ice sheets. Right? Now, also in high mountain areas during the Pleistocene was the growth of enormous alpine glaciers. And so, many have melted back, but there are still a lot of really great examples of alpine glaciers today. Probably the shrunken remnant of what was once the larger Scandinavian ice sheet is the small ice sheets on Iceland today. That's probably about it. I want to talk to you about just two interesting, noteworthy features of glacial ice if you ever do some traveling. Uh, True glacial ice has a beautiful crystal blue color, and this is an alpine glacier that really has been melting back in Switzerland. It's in near the town of Grindelwald, and it's called the Grindelwald Glacier. And we were there. There were some actually ice climbers there. But the Swiss Park Service kind of cut a hole in, and you can go into the tunnel and see the beautiful crystal blue color of true glacial ice. And then they kind of cleared off the dirty surface, and you can see the blue color. Now, another characteristic feature besides the crystal blue color of true glacial ice is the surface of all glaciers. They have deep surface cracks because as the glacier moves, I mean, the surface is rigid ice, and the ice is going to break up and crack. Now, the term for these deep cracks, it's kind of a French term. It's crevasses. It's not just crevices, it's pronounced crevasses. And so there are deep cracks on the surface of glaciers, and you can see in the background here. Now, hiking on glaciers is very dangerous because of these crevasses. They can extend down hundreds of feet. And very often, as you can see here, they can be obscured by a recent snowfall. And so you can take one wrong step, and you are down a deep crevasse hundreds of feet. So these hikers are wearing crampons, on their boots, and their spikes, and basically they're all tied together. So if someone falls down a crevasse, hopefully they'll be able to pull them on out. All right, let's talk about the landforms of ice sheets. What we're going to try to think about is the Laurentide ice sheet of North America. And we're going to talk about the erosional landforms that ice sheets create. And basically, it is kind of pretty straightforward. What a mile thickness of an ice sheet will do will just take all the pre-existing soil, all right, and incorporate it in the ice. And it'll just remove all the pre-existing loose soil and loose rock and right down to bedrock. And very often, the bedrock that we see today is kind of scoured, right? You kind of see striations and grooves, right, as evidence, of the glacier movement. So a lot of times you can actually see the direction in which the glacier moved. And this is a classic, glacially scoured landscape, where all the soil is removed and you've got bare bedrock everywhere. I'm going to talk to you a little bit more about erosional features. So not only did the Laurentide ice sheet and, of course, the Scandinavian ice sheet, remove all the pre-existing soil and erode down to the bedrock, it actually eroded deep into the bedrock, creating hundreds of thousands of glacial lakes. And here's a map of North America, kind of showing you, where lakes are. And really, by and large, I would say, probably about 95% of all the lakes in North America are definitely related to glaciation. So here's, this is basically all Canada. There are so many lakes, hundreds of thousands of lakes in Canada. They haven't even named them all. And extended into Minnesota, the land of 10,000 lakes, and there are lots of lakes in New York and New England. Now, there's some sinkhole lakes here, the Great Salt Lake, and Louisiana has a lot of lakes related to Oxbow Lakes, the river and the marsh. That's not really shown here. I just want to kind of show you. Here's a map of northern Minnesota. The land of 10,000 lakes, or Land O'Lakes. I mean, this is a dairy area if you ever buy Land O'Lakes butter. And here's just a little aerial shot of Canada. And just so many lakes and lakes and lakes. So that's another, feature. Bare bedrock, and then lakes scour into the bedrock. And speaking of lakes, the Great Lakes, these enormous lakes were created by the Laurentide ice sheet. And this was originally an area of very weak rock, weak shale. And the Laurentide ice sheet, during its advance and retreat, found it very easy to scour and erode away this weak shale. And so here we've got pictures of the last glacier, melting on back, into the Holocene. And if you kind of take a look at the shape, maybe even of Lake Michigan, it's actually the shape of a glacial lobe. So that's kind of interesting. Now there is another kind of very famous lake. Besides the creation of the Great Lakes, are Finger Lakes. Now there are Finger Lakes, throughout Scandinavia. They're very famous there, and there's a famous Finger Lakes region of central New York State. There are also Finger Lakes in Wisconsin and Minnesota too. And so they're elongated lakes, and they're very, very deep. Hundreds of feet deep. Like the Great Lakes too are very, very deep. Deep glacial scour, 500, 800, 1,000 feet deep. And so they're not, like Lake Pontchartrain, which is 15 feet deep. We're talking about, hundreds of feet deep. And so this is a satellite image of the Finger Lakes region in New York. And what you had to have are river valleys flowing in a particular direction. And we know that a river valley is an area of weak rock, probably shale. And the other thing that you needed to create a Finger Lake is you have to have the glacier advancing in the exact same direction. And so it was very easy to take that weak shale in those river valleys and scour them out very, very deeply. And so you wind up with elongated and very, very deep Finger Lakes. And this is Seneca Lake in beautiful New York State in central New York. That's just one of the lakes. And it's very deep. All right, so those are the simple erosional landforms of ice sheets. Now, a lot of that eroded material became deposited eventually once the ice, melted back. So let's talk about some of the depositional landforms created by the ice sheets. And so here we've got a diagram showing the ice lobes, and they've since melted back, and some of the characteristic deposits that we can find today, north of the Ohio and Missouri River. All right, the basic feature of depositional landforms of ice sheets are called moraines. Now, this is just unsorted debris. Unsorted, so giant boulders, rocks, cobbles, down to sand, silt, and clay, just totally unsorted debris, basically bulldozed along and pushed along by those mile-thick ice lobes. And now so there are a lot of different types of moraines, and I'll just give you a couple of them. There's something called the terminal moraine, and that marks the farthest advance that the glacier ever moved. All right, so here's the terminal moraine here. So it just kind of bulldozed along, and it just, then the glacier just melted on back and left these ridges of debris. And so they're, a couple hundred feet high, maybe 1,000 feet high at most. And they kind of, very often outline. This is kind of how we know they advance as lobes also, plus the shape of the Great Lakes, kind of have a lobate form. And then there's another kind of moraine called recessional moraine, and that's illustrated here. And that's when the ice lobes were retreating and then surged forward. And so again, kind of bulldozed some more debris and then left it again. But you're always going to find recessional moraine behind the terminal moraine, because the terminal moraine, marks the farthest that glacial ice ever went. Here's a geologic map centered on, the Great Lakes area, of course, that were created by the Pleistocene. But it also shows the moraines. And the moraines are shown in this kind of olive. And look at this beautiful ice lobe here. So we've got terminal moraine and all these recessional moraines. Terminal moraine right in through here. It's all this olive green. And then a whole bunch of recessional moraines and moraines and moraines. And also, this is the driftless area. You can see that there's no real green coloration or anything there. There's no glacial drift there. Except, there's where rivers, in their alluvium have carried some glacial drift. But there's the driftless area there. Yeah, so this is when you go to the upper Midwest. It's basically, the agricultural heartland of the United States. It's the corn belt and dairy belt in the upper Midwest. And so you usually think of the upper Midwest as being flat and agricultural. Well, actually, the flat agricultural land is interrupted by moraines. And I've got some moraines here in Wisconsin, which is in dairy. You can see the dairy farming here. And this is what a moraine looks like. So I don't know how many, a couple hundred feet high. And here's another moraine and they have some state parks here. And then here's actually an aerial view of a moraine here, all right? And so there's the agriculture, and this is kind of curving around. You can see it's kind of in the shape of an ice lobe. And, where you've got boulders and cobbles and clay, and it's just all hummocky, debris piled on up. Of course, you can't cultivate it. So that's how you can always tell when you've got a moraine when you're traveling in the upper Midwest. Another depositional feature is called a drumlin. Now, drumlin is kind of a funny name, but it was coined by Irish geologists, studying glacial features. And so drumlin is Celtic Irish for streamlined oval hills. And that's what a drumlin is, streamlined oval hill. So it's not just any pile of dirt. They're very streamlined. And it's believed that what wound up happening is, so the glacier deposited its terminal moraine and a whole bunch of recessional moraines as it retreated back. And then it's believed that the glacier must have advanced again over that moraine and retreated and advanced and retreated several times. And it wound up reworking all of that recessional and terminal moraine and wound up reworking it, into these kind of oval-shaped features called drumlins. And here's one near the Finger Lakes region, actually, of central New York State. And you'll never just see one drumlin, all right? Since those ice lobes were huge and they advanced and retreated, usually they're going to recycle all of that moraine material into hundreds of these oval drumlins. And here's one in Wisconsin where there's contour farming. And we visited one of the state parks in Wisconsin, is Cayman Kettle State Park. And we were on our way, we saw Drumlin Drive. We took a little detour on Drumlin Drive, and what do you know, there's a beautiful drumlin here. All right. Another landform is called an esker. And again, this is Celtic Irish too, by Irish glaciologists. And what it is, it's a sinuous hill of sand and gravel formed by a river in an ice tunnel. And so what they are hills, maybe 50 or 100 feet high, and they're sand and gravel. They're alluvial deposits, and they're meandering, okay? They're meandering. And so there's one in South Dakota, and here's one in Wisconsin. And the way they formed in ice tunnels at the base of the ice sheet. Really, you think about, a mile thickness of ice, all right, scraping against the rock of the ground. There's a lot of frictional heat that's created. And so you've got a lot of meltwater, circulating at the base of the glacier. And that's actually how the glacier moves, it's kind of sliding along, on that meltwater. And it's just kind of so interesting that meltwater somehow accumulated into low spots and formed meandering streams underneath the ice. Now, the moving water, melted the ice and created ice tunnels. And, all of that meltwater at the base of the glacier was also carrying, sand and gravel. And so the river then, in this ice tunnel, was carrying, its bedload, sand and gravel, alluvium. And so today, what you wind up with, are 50 or 100 foot high hills, representing these former rivers meandering under the ice in ice tunnels. And here's some ice tunnels here in Alaska, and some crevasses in the blue color. The final landform is glacial erratics. And these are usually giant boulders, not related to the local bedrock. And so the ice, plucked out like a giant boulder up in Canada and carried that boulder, all right, hundreds of miles to the south. And the glacier melted and just literally dumped a giant boulder, right, in New England or the upper Midwest. And so basically what it is a big giant rock that's unrelated to the local geology. Now, virtually all of Canada is granite. And so, these glacial erratics, these big boulders, are granite. And so, if you're in an area of hundreds of miles of limestone or hundreds of miles of sandstone or something like that, you would imagine that if there was a boulder sitting around there, it would be from the local geology. And so this, is, so when you go to New England, you see the colonial mansions, there are always invariably giant glacial erratics in the yard. And actually, a famous Plymouth Rock is a glacial erratic. I always thought it was much larger than this. Look at that, they've got it caged, right? I guess, it's not going to attack us. I guess we're going to attack it. And actually, I just took this picture over the summer up in Massachusetts on a hike with my sister and husband. But there's a beautiful glacial erratic here. They're giant. And actually, there were about 5 or 6 of them in the area. And so they're really common, in glacial areas. End lecture.